Okay, welcome back. This is the second video following up with the simulation for hypothesis test for the difference of two proportions. So it's the same scenario. In the last video, we just set up the hypotheses, okay, and we did a simulation using my computer program um, to estimate or predict what our conclusion should be. And we ended up saying that, if we anticipate that the true proportions are in fact equal, that there is no difference between the proportion of yes voters in 2008 and yes voters in 2007, which you can also write like this, which I prefer for statistics. This is preferred for sense making. Um, so you can write them either way, they're both acceptable. But if we anticipate or we expect them to have no difference, then it makes sense that when we take random samples, that the differences in like the sample proportions, the p hats, should be close to zero. I mean, if there is no difference truly between the two populations, then the sample proportions should roughly have no difference between them. So when we did this and we did our simulation, um, our actual data, here's what is expected. We expect a zero difference. Our actual data was that we got uh, the actual observed difference, our statistic was 0.06. So if we look at this, where does 0.06 fall? 0.06 is way out here. It's pretty rare. So its probability, I think we said it was maybe 2 out of 1,000 because there's 1,000 simulated random samples from two populations here with the differences in their proportions. There's 1,000 statistics here. um, 0.06 or bigger, more extreme, probably only occurs about 2 out of 1,000 times. So what does that mean? That's super rare. So if we anticipate a zero proportion difference and we get actually a 0.06, which is 6% difference, um, according to what we have, that is far enough away to be rare from what we would expect. And so our conclusion should be that, we think that the proportion has actually increased over the year. And then, so we can argue that from looking at the simulated distribution and where does our actual statistic fall on that distribution and how likely a statistic more extreme than that is to occur. So this would be our simulated p-value would be about 2 out of 1,000 because there's only a few of them that do occur at 0.06 or beyond. So we're going to reject our null hypothesis, and we'll write that conclusion in a second. So the rest of this video is how we actually run this formally without a simulation, and we're going to do another problem with it, and we're also going to use the calculator. So the first problem here is going to be done without the calculator, except for doing some calculations, and the second problem we will do with the calculator. Because you need to understand the statistics behind it. So first of all, we set up our hypotheses. Our hypotheses were that there is no difference in proportions, but they said that they want to know, do they think that this proportion has increased within the year? So this is equivalent to saying that the proportion in 2008 is greater than the proportion in 2007, or that difference in this order is greater than zero. In the last video, I did not have a significance level here because I was trying to just make sure we focus on the simulation. Significance level alpha, that is our probability cutoff. A probability or a p-value less than 0.05 will allow us to make one conclusion, and then a probability greater than 0.05 will allow us to make another, or result in us with a different conclusion. So we'll look at that in a minute. For a complete and full understanding of a hypothesis test, this must be defined, all of that up here. You must define your parameters. So we defined those in our last videos. What does P with the subscript of 2008 mean and P with the subscript of 2007 mean? You could use P1 and P2 if you want, but you have to define them in context so everybody knows exactly what you are talking about. You have to check conditions. So in the last video, I said for me, when we have two samples, I think the best way to do this is organize in a little table where, and I remember I learned this for myself last year when I was grading the AP exams on a similar question to this. I saw that, clearly one teacher had their students organize it in this way, and I really liked it. So for two samples, I think this helps organize your conditions. You need two random samples. You need to have these conditions checked, n times p hat n in 2008 times p hat in 2008. Same thing with n times 1 minus p hat, and over here with 2007. You must show your work. You must write these out. You have to check them, and make sure they are both greater than 10. This is your normal check for each population. So we can use the normal distribution now to solve our problem, because our expected successes and failures in each, or the number of successes and failures, in other words, the number of yes votes and the number of no votes, were at least 10. So we can use the normal distribution, and we have independence. So our sample size in each year is certainly less than 10% of all the adults in the United States, which means that all of these respondents are likely to be independent. I mean, it's really unlikely that you've picked someone, the same person in both years, and family members or things like that. I mean, there's just such a small percentage of the United States adults. So we have our random sample check, normal check, independence check. So we can proceed. We call this test that we are going to do. So we can, the type of test this is a two-sample z-test for the difference in proportions, okay? Or just two-sample z-test for proportions, however you want to write it, but you must say the type of test we are going to do. Two-sample z-test for proportions, or for the difference in proportions, and we'll look at that here in a second. And on the calculator after when we do the second problem. So you have a statistic that's calculated. You have two samples. So you have a statistic for the first sample, which is p hat in 2008, which was 0.67, which means 67% of the respondents voted yes. And in 2007, 61% or 0.61 of the respondents responded yes. So the statistic we are interested in is what is the difference in those 2 years. So I took 0.67 minus 0.61, and I calculated the actual difference that we observed when we took the sample. So we observed a 6% difference in our sample proportions for 2008 versus 2007. And so we need to figure out now, is this actual difference far enough away from what we do expect to happen? So the question is, what do we expect to happen? Our initial expectation is that the proportions are equal. And if you think about it, until you take random sample, when you go into 2008, you don't know if things have changed. So your best assumption in your expectation is that they're the same, that nothing has changed. So this is our initial expectation, our null hypothesis. So when you come down to here, it says, my question is, so what do we expect our sampling distribution of the sample proportions, I should have in here, of the difference in sample proportions to look like? What do we expect that to look like? Well, if you look at my simulation I did earlier, I would say this is going to look pretty darn normal, right? I mean, normal, maybe the mean looks like it's centered around 0 with some sort of standard deviation. I mean, logically, right, you should expect it to be 0. You should expect the mean to be 0, the expected value. Why? Because if we expect there to be no difference in the proportions, then when you take a sample from each year, you should expect to get about the same proportion of yes voters. So it makes sense that the average or the mean or the expected difference is 0. We already talked about why it's normal, because of your checks and the conditions. And then we got to find the standard deviation. So I'm going to refer you to your formula sheets. Your formula sheets. These formula sheets are what you have. This is the new one that AP is allowing for the AP test. You also have one that I gave you. But here in our formula sheets, this is why you need to learn those earlier in the year. And we had those quizzes on it. For two populations, the statistic, the random variable you're interested in is this right here, the difference in p hat 1 minus p hat 2. The expected value of that difference is the true difference in proportions. Here's your standard deviation for that distribution. And then we have the standard errors over here. So Um, so what we need to do is we need to calculate the standard deviation for our normal distribution. Okay, the problem we have is in our problem, we actually don't know um, what these proportions are. We don't know, like this would be P 2008 and P 2007. We don't actually know what those are because we just have sample data. We don't have population parameters, and so this is a problem. So we can't use this formula here to calculate that because we don't actually know what P1 and P2, or in our case P 2008 and P 2007 are, because we don't have those actual population proportion, those parameters. Okay, so we come over here and we look at it and we're like, oh, okay, we've seen this before and we've used this to calculate a confidence interval. This is the standard error of this difference in sample proportions. We've used this before. So we could put in here p hat 2008, p hat 2007, and calculate our standard error. And do that calculation, which is what we had done in the past. Okay, so there is one little caveat to it, and this is one thing that we had not discussed yet. We can do another. There's another way to calculate standard error, and it's to use this formula right here, which I'm going to explain in our problem in a second. Notice that it's very similar to the one up here, but it is used when you assume that P1 and P2 are equal. So in our problem, we are assuming that we expect that P in 2008 is equal to P in 2007. So the proportion of yes in both years is the same. So this is our formula we're going to use for our standard deviation, for our standard error. And this thing right here, this p hat with a little c, it'll make more sense. This is the combined sample proportion, and we're going to use that to estimate in our formula. So what this looks like is with our actual data. So this standard error, in summary, this standard error is used for a confidence interval. This standard error we will use in our class for our learning purposes when we do a hypothesis test for the difference of two proportions. So confidence interval, and this will be for a hypothesis test. Okay, so let's look at what this looks like. Okay, so we know the mean is 0. Standard deviation. The standard deviation is approximately this thing, and I put in this formula, this is what this looks like, and I'm going to try to make this a little bit bigger for a second. So this thing right here, if you notice, I put in here p hat c and 1 minus p hat c, 1 minus p hat c, because really what we're doing is we're taking this formula up here and we're substituting instead of P1 and P2, P hat 1, P hat 2, we're going to use this new statistic we calculate in its place. And this is how I like to write it. I prefer to write it this way because it drives home the point that you are still using really the same formula with just a different statistic. The AP writes it like this just to simplify it a little bit. But all they have done here, and I hope that you can recognize this, is that they have factored out this common factor of each term and pulled it out front. So this is your formula. There's nothing different for it. So this is our calculation. So let's talk about this p hat c for a second. What is that? Okay, this is called the pooled or combined sample proportion. And so it's like, why are we using that? Like, we know what p hat for 2008 is, and we know what p hat for 2007 is. Like, why don't we just use those in this formula and calculate our standard deviation or standard error, which is estimates our standard deviation? Well, the reason we don't is because you are making one big assumption and one expectation in this problem, and we expect the proportions in each year to be equal. So what we do is we make a combined sample. Okay, we treat this like these two samples we have, which one of them had 1,009 people, the other one had 1,020. We treat them as a total sample of 2,029 people, and we calculate the total number of yes voters in that sample, which is 1,298, and we treat them as like one big random sample from these populations that supposedly have equal proportion of yes voters. And and that's why we do it. We use this to estimate what we think the actual equal proportion should be. Um, so that's why we use it to give that, because of our assumption, and it's because we expect the population proportions to be equal. So we use that in our formula, and everything else is pretty much the same. So you substitute that in, do a little calculation into here, and we get 0.02132. So our standard deviation that we are going to use is 0.02132. Okay, so we know our distribution is normal. The mean is 0. The standard deviation is about 0.02132. This is our pooled or combined sample proportion. And so let's look at what would this picture look like. If I go to my normal distribution and I draw this picture, it would have a mean of 0 and a standard deviation that we just calculated, and it would look something like this. Okay, so this is what we expect our distribution to look like. So you can draw that for yourself. This is our expected distribution, and it really should. It resembles what we had in our simulation. Look at, I mean, it's centered at 0. You see like negative 0.05, 0.05 out there. It looks fairly similar to what we would expect to occur even through our simulation. So this is our distribution that we're going to use to solve our problem. So we have our normal distribution. We know what that is. Our test statistic. So really all that's left is we're going to do a p-value calculation, which is just a normal distribution calculation. We're just going to find the probability that our statistic is at least what is greater than or equal to our observed value. This greater than or equal to comes from our hypothesis, because we are checking to see if we have an increase. So we find the probability to the right. Our statistic we calculated for this was p hat 2008 minus p hat 2007. That's what our statistic was. And that value was 0.06. So we want to find the probability of that this difference is at least 0.06 using the normal distribution that we established. And that is normal CDF, lower bound, upper bound. The expected difference is 0. The standard deviation is that. And if I go up here, I'm going to use this to do it because you guys know how to use your normal distribution or normal CDF. I put up here 0.06, calculate the probability bigger than that, and I get 0.00244. So this p-value is 0.0244. So this is the probability that we observe a statistic of 0.06 or more if we expect the proportions to be equal. So this is super small probability. Our p-value is part of our conclusion, 0.00244, which if you notice when I did my simulation earlier, if you remember me saying, this looks like maybe there's just like maybe 2 observations out here. 2 out of 1,000 is consistent. This is 2 1,000ths. Our conclusion is, since our p-value is less than our significance level, which is our threshold probability, so less than 5% chance, we reject the null hypothesis that the proportion of voters of yes respondents in 2008 is equal to the proportion of yes respondents in 2007. We have evidence, which is your sample data, to suggest that the proportion of yes respondents has increased, which is your alternative hypothesis. Over the year. Okay, so that is our conclusion. I skipped this test statistic part for a second. We're gonna calculate it because that's just a z-score. Some of you use the z-score to do your normal calculations. So your z-score would be your statistic, which is 0.06, minus the parameter. Now the parameter, and this is off your AP formula sheet. You can see that up here. Standardized test statistic is right here. Okay. Your parameter is your expectation. So our expected difference was 0 from our hypotheses. The standard error was 0. What did we calculate? 0.2132. And that value we can just is 2.814. I mean, that's almost 3 standard deviations above what is expected. And if you know your empirical rule, when you get to 3 standard deviations on the normal distribution, you become that value becomes pretty rare. So that is our test statistic, p-value, and our conclusion for this. So this sample data would suggest that the proportion is actually increased. So this is the raw statistics behind all of this. The next problem we're going to do is not going to involve all of this calculation by hand. We are going to use the calculator to do it, so you could see what would be an appropriate response and what you actually need to set up for some sort of hypothesis test like this. So, and I will link this document to our problems, to this video, I'm sorry, after I am done. So let's take a look at this one. In order to monitor, change that to like 175. In order to monitor populations of birds on a particular island, the following procedure is implemented. So they this is called capture recapture. So some of you in biology might have heard of that. Captured an initial sample of 200 birds from the specified from the species on island A. They attached leg bands to each of them. They released the birds. Similarly, a sample of 250 birds of the same species on island B was captured, banded, and released. Sufficient time was allowed for the birds to return to their normal routine and location. Subsequent means samples taken again the next time of birds of the species of interest were then taken from each island. The number of birds captured and the number of birds with leg bands were recorded. The results are summarized in the following table. So they took, from island A, they took a sample of 180 birds. 12 of them came back banded from the previous sample. And then island B, they took a sample of 220 birds, and 35 of them came back with having banded legs. So assume that both the initial sample and subsequent samples were taken on each island can be regarded as random samples from the population of birds of the species. Is there statistical evidence that the proportions of banded birds differ on each island? So when you see is there statistical evidence, this is referring to a hypothesis test. You have to conduct a hypothesis test to answer this question. So let's define some things here. So I'll use like green for this. Okay, so let's define a few things. First of all, your parameters and hypotheses. So your parameters. What are some things we need to define? What are we interested in? So first of all, we are interested in P. We're interested in 2 proportions. P sub A, which is the proportion of all birds of this species on island A. And then we have the same sort of definition for PB, is the proportion of all birds on island of this species on island B. Okay, so we're looking at a specific species. We're comparing, for example, let's just use seagulls. We have so many around here. the proportion of seagulls in Cleveland to the proportion of seagulls at like Kelly Island out in Lake Erie. So that could be your two different land masses, okay? You're comparing the proportion that you think is there. So those are your proportions, those are your parameters. You need your hypotheses. Okay, so your null hypothesis. What do you expect to be true? Well, before you do anything, I mean, before you do any sort of data, and this research group, you expect that the difference in proportions is zero, like that there is no difference. Okay, so that would be the same as writing, and again, it doesn't matter which way you write this. You expect that the difference in proportions of birds on those islands are the same. What is the alternative? So it comes right here. They want to know, are the proportions different? Do they differ on each island? So that means our alternative hypothesis is that we have a not equal to. Alternative, that this difference is not zero. In other words, don't know if it's bigger, don't know which one's bigger, don't know which one's smaller, but we're going to go ahead and say that they're probably not equal to. So that's going to be our alternative explanation for these people when we're done. So you have your null hypothesis, your alternative hypothesis. It doesn't give us a significance level. So if it doesn't give you a significance level, you have the freedom to pick your own. Generally, we pick 5%. So we'll use alpha. You set your significance level. Alpha equals 0.05. You got to check your conditions for each of these samples. I'm going to copy and paste this table down to save a little bit of time. Check your conditions for each sample. So you have to set this up. You got your conditions here. Okay, for island A and island B, okay, they said you can regard these as random samples. Told you that. It was given to you. Random sample taken on A, random sample taken on B. No, that's true. Okay, over here we got to find, check these numbers out. The sample size for island A times the sample proportion for island A, and then same thing with A over here and B. Okay, so when we do this, so we come up here. Okay, so what do we know? We know that the sample size for island A was right here, 180. Sample size for island B is 220. So we know this is island A was 180 birds. This one was 180 birds. This was 180, or this was 220 for island B, 220. Okay, let's calculate the sample proportion. So the sample proportion for island A was, we had 12 out of 180. So this proportion is 12 out of 180, which is 0.067, and we know the sample size here was already 180. We have to take these numbers and check them. So this is 180 times 0.067, and then 180 times 1 minus that, which is 0.933. And you calculate those numbers, and you should get about 12 and about 168 over here. They are bigger than 10. We do the same thing over here. So the sample proportion for banded birds for island B was, what did they have? They had 35 out of 220. So you got 35 out of 220. That was about 0.159, so a little under 16%. The sample size over here, which we already said was 220 birds. Did that. So you got to check your n times p hat. So 220 times 0.159, and then 220 times 1 minus 0.159. So that's about 80.84. Okay, when you calculate those, you should get about 35 and about 185. Those are all bigger than 10, so this is our normal check, so we can use a normal distribution. Okay, the next thing here is we got our independence check. The sample size for island A was 180 birds. That's probably reasonably less than 10% of all birds on that island. I mean, if we're assuming we have a pretty large island, that's pretty reasonable. 220 over here for island B. That is probably reasonable. 10% of all birds on island B. That's also pretty reasonable, just because there's probably a lot of birds on that island. So that means all of our birds are independent of each other. So it doesn't take too long to check these. I'm typing them and talking at the same time. Conditions go pretty quick. Okay, now that you've checked your conditions, all of them are met, you are allowed to use, so we can use a two-sample z-test for proportions. Usually we like to say the difference of proportions, because that's what we're testing. And we're going to use our calculator to do this. So at this point, we're going to go find our test on our calculator. It's going to give us our test statistic. It's going to give us everything we just did up here, and we can make our conclusion. All right, so it's kind of nice. So you go to your calculator, and we find our test statistic stuff. So if you go to stat and test, and I encourage you to use this thing. So I put a video out there about confidence intervals. So this is one, how to use your calculator for hypothesis test. You find it right here, two proportion z-test. This name is in fact acceptable for full understanding if you write that. So you can also call this a two proportion z-test. So we come down here to two proportion z-test, and you enter your data in. So x1 is the number of banded birds. So we're going to say 1 is island A. So in island A, the number of banded birds, what did we have? We had, use this table, we had 12 and 180, and then 35 and 220. So 12 is x1. N1 was 180. X2 was 35 for island B, and 220 was the sample size in island B. Okay, what is our alternative hypothesis? Our alternative, if you look at it, what do we have here? When we wrote this, the alternative hypothesis was a not equal to hypothesis. So P1 would be PA and P2 would be PB. So we would pick the not equal to. Not equal to, go down to calculate. If you hit draw, it's just going to draw the normal distribution for you and give you the probability. Calculate, and here we go. So gives you your test statistic. This is your z-score. This is based on the difference in your sample. So you have your test statistic. This p is your p-value. If you run this on your calculator, all of this data needs to be recorded in your response. So I'll put that up here. All of this has to be recorded. You've already done some of this recording, so some of this is not necessary to write down. I'm just copying it over to help you all out for understanding this. Bump that up. Okay, so here's our data that we get from our calculator. All right, this is your test statistic. That was calculated in the exact same way we calculated this z up here, just with a different scenario. This p without the hat is your p-value. Okay, p hat 1 was for island A. So if you look at island A, it's right here. It's the same thing. P hat 2 was for island B. Those are already recorded in your setup, so you're okay. You don't have to re-record that. Okay, this P hat, this is the P hat C, the combined proportion. You do need to record this. So this has to be recorded as part of your response. You've obviously already recorded. The sample size is way up here, so you don't need to worry about that. So from your calculator, what you need to record is what your z-score is, negative 2.856. You need to record your p-value. 0.0043. And you do need to record the combined sample proportion, or the pooled sample proportion of banded birds. And we denote that with little c. And that is 0.1175. Okay, and then from here you have all your statistics. You've named the type of test. You've checked your conditions. You just got to make your conclusion. Your conclusion. So you take your p-value, you compare it to alpha. We set our significance level at 5% again. So since 0.0043 is less than 5%, in other words, this is a rare difference. And look at the actual difference here. The actual difference in proportions between the two islands is almost 10%. Like, so this is saying that, you know, maybe island B has a little higher proportion than island A. But so we have that off our calculator. Our conclusion is, since our p-value is less than our significance level, we reject the null hypothesis that there is no difference in the proportions of this type of bird on islands A and B. We have evidence, which is our sample data, to suggest that there is a difference in proportions of this type of bird between the two islands. Okay. Your alternative hypothesis was that there is a difference, okay, that is not equal to 0, that they are not equal to each other. Your alternative hypothesis is not that not that B is bigger than A or vice. It's just that they are not equal. In other words, there is some sort of difference between them. So that is your conclusion. That would be your whole hypothesis test. They go pretty quick. The hardest part, the longest part is checking your conditions. The rest of it is running it using your calculator. And we should be good to go. So if you have any questions, please let me know.